Hello, it's Keith here, and this is lesson 8 of the platform-specific series of my Z80 programming tutorials. Now, over the last two weeks, we've been looking at the Game Gear hardware, the Master System hardware, and the Game Boy and Game Boy Color hardware in some detail. However, we hadn't actually started to program those systems yet. We're going to start properly today, and we're going to have a look at the example I showed before, this one here, and we're going to have a look at how the graphics are got to the screen. These examples don't use sprites, they're all done with the Tilemap, so we're going to look at how to define a font as the Tilemap and how to load in a bitmap from file and then display that to the screen on the Sega Master System and the Sega Game Gear. And if you've not seen my previous lesson discussing those systems, they're actually essentially the same system. The only difference is the Game Gear screen is slightly smaller and it has a slightly more complex palette definition. But apart from that, the code that runs these two is identical. The example files for today's lesson are available on my website as always, and as usual there is a text-based copy of today's lesson on the website as well if you prefer to read rather than watch the video. So anyway, let's have a very quick look at the source code. So this is the code that runs on does today's lesson with regards to actually using the functions to draw the sprites onto the screen. You'll see we've got a file defined here called raw SMS because the bitmap format is the same for the Master System and the Game Gear, but this code will actually get it to the screen. But it's not this we're going to be looking at today. We're going to be looking at this sort of more hardware level code that is working just on the Master System and the Game Gear, because this is actually generic code which will work on the Master System, Game Boy, Game Boy Color, Game Boy Regular, also the MSX1, MSX2, and the V9990 as well. It should work on that as well. So this is quite generic code, and so we're not going to look at this today apart from how we actually use the functions like this fill area with tiles function and this define tiles function, which are the real platform specific stuff we're going to be looking at today. So let's make a start then. The first thing to understand about the Master System and Game Gear hardware is that they use a separate graphics chip like the MSX, and just like the MSX, it's called a VDP. It's actually compatible with the MSX1 graphics chip to a great extent. So the memory of the graphics chip is separate to the Z80's addressable range. So that means we have to use out commands to tell the graphics chip what memory we want to write to, and then more out commands to send data to the graphics chip. Now on the Game Gear and the Master System, it uses 16 kilobytes of memory. So the address range is 0000 to 3FFF. We use the command port BF when we're writing data to the graphics chip to select a memory address, and all we do is we send the low memory address, then the high memory address. But one slightly odd thing, we actually have to add 4000 to the memory address. So we effectively add 40 to the H part of the memory address, and that tells the VDP chip we want to write to that address. Also, if we set the memory address to C000, this will start pointing at the palette entries. So C001 would be the second palette entry on the Sega Master System, or the second half of the first palette entry on the Game Gear, which has a more advanced palette. We're going to look at that in a later lesson though, but I just wanted to briefly describe it as we were going to have to start talking about memory addresses. But C0000 isn't a true memory address because it does only have 16 kilobytes of memory. It's more like a command to point to a memory than a real memory address. Okay, so that's the first thing, is the addresses of the memory. The other thing that's quite interesting for someone coming from systems like the MSX and the Sam Coupe is the structure of the memory in 16 color mode, which is the main mode of those systems. Now, if you imagine you had 8 pixels on the screen that were consecutive like this, on systems like the MSX and the Sam Coupe, each pixel is defined by a set of 4 bytes that make up a single nibble. So the first byte we write to the screen would set the colours of pixels A and B. Then the second one would do C and D. The next one would do E and F, and so on until we've set all of 8 of the pixels. Now, on the Sega Master System, and this is also true on the 4-color Game Boy, that's not how it works. It works in bit planes, and so you're effectively setting part of all 4 pixels with the first byte you write, and then the second byte sets the next bit up in the colours definition, and then in the 16 colour systems you have a third and a fourth bit plane byte. So you can kind of imagine, if you imagine a nibble having 4 bits, and the first bit is bit 0, which is worth 1, the second one bit 1, which is worth 2, bit 2, which is worth 4, and bit 3, which is worth 8. These would be made up of the 4 consecutive bytes that you wrote. So the first byte of the bit plane that you send to the Sega Master System or Game Gear will define the bit 0. The second will define bit 1, which is worth 2. The third one bit 4, and the fourth one bit 8. But if this is all a bit confusing for you, you don't need to worry too much, because if you look at my Aku Sprite editor, which is part of my sources download, there is an export function which will export in the format that you need for the Master System and the Game Gear. This Sega Master System function does both, and it will export in the bitplane format that you need. And that is how I've created the bitmap that you see on the screens that I showed earlier. The colours are wrong because we're not defining a proper palette, but I can assure you that is how it looked. That is correct. It's being exported correctly. We're going to look at palettes in a later lesson though. So what do we need to do first? Well, when it comes to using the Master System, of course, we need to do a bit of setup first. So the first thing we need to do is we need to tell the system, the Master System or the Game Gear, that we want to use the 16 colour screen mode, because as I say, it does actually have this rather strange MSX1 compatible screen mode, which is vastly inferior, so we don't really want to use it. All we do is we send these default definitions to the various registers that define the screen settings. Now, generally you won't want to change these. You might want to change the border colour maybe, but we're just setting it to black. But one thing you might want to bear in mind at least is that some of the memory addresses can actually be reconfigured. So I've put kind of the default ones here, and these are pretty good for general purposes, but in some cases some of these can be moved around a bit. So if you have a need to reposition them, or you want to use some of the memory for an alternate purpose, like maybe you want to have 2 tile maps and swap between them or something, there are some options to allow you to do that kind of thing. But for these tutorials, we're going to stick to these default ones, which are generally the ones you're going to be using. So now we come to the discussion of how we're actually going to get the graphics onto the screen. As I've said, this example here entirely uses tiles. There's no sprites involved. The main reason for that is that sprites are very limited on these systems. You can only get, I believe it's 40 sprites on the screen at one time. Now, of course, you can fill the entire screen with tiles, and on the Master System and Game Gear you have up to 512 definable tiles, so you've really got a lot of flexibility. So what we're doing in these examples is we're using the first 96 of the tiles from 0 to 95 to define a basic character map for these letters here, and we're using the same 2-bit font that we used for our Spectrum and our Amstrad CPC earlier, so we're using the same code again for that, the same bitmap data, sorry, for that, but we're just using new code to convert it to the Master System's bitplane format. And then when it comes to the sprite, we need that that correct bitplane format, which we created with the exporter. And then what we do is we fill this area with tiles that aren't in use by the font, and in my example I'm starting from 128. And then we define those tiles to be the bitmap data that makes up this Chibiko character here, although she's looking rather red today. Her skin should really be white. So as I say, the palette's pretty far off, but the sprite is perfect. So sorry, I shouldn't call it a sprite because it's a tile map, but the bitmap data is perfect. That's a more appropriate way of defining it. So as I said, just use the my sprite editor to export this if you want to play with this. So let's have a look at the code here. So when it comes to actually selecting a memory address, we've got this prepare VRAM. Now, I only ever write to video memory. I never read back from it, because really you should never need to read back from it. If you've got sprites on the screen, you shouldn't be reading video memory to work out where they are. So as I say, I only ever write to bitmap memory, to VDP memory, not read back from it. And for that reason, I'm ORing in 40 into H here, which, as I said before, tells the VDP we're writing data. You could create an alternate version of this with this missing, and that would read from the VDP using the in command, but we're not going to be doing that in this example. I've got a very basic clear function here, which we use at the start just to wipe out any junk from the memory, but really you shouldn't really need to do that because the memory probably is blank anyway, but just for safety we wipe it out. We've got a function here called write to VRAM times 4. You'll notice this sends a byte from HL, and it sends the same byte 4 times. Why do we do this? Well, this is for our font. If you remember, I said our font is only 2-bit. Because of the font is basically in Spectrum format, which is just black and white. Now, on the Sega Master System and Game Gear, we need a 16-color font, and we need 4-bit planes. So by writing the same value 4 times, we're basically setting all the bits of the color definition to 1, thereby selecting color 15, which is quite a nice way of doing things. We're actually using color 15, or the top color on the 4-color system, so color 3, on all of the systems now, just to make things consistent, which was part of the work I did for the Grime project. I wanted to have everything nice and consistent and look the same on all the systems. So that's what the write to VRAM function there does. Now, when it comes to actually getting the data to the tiles, we need to do some work first. So if you have a look at this example here, define tiles is what actually does the work of setting the sprite data, so the chibi code bitmap character. And what we need to do is we need to work out where in memory we're going to write to. So here's the example on the Master System and the Game Gear. And the first thing I noticed is that I was apparently lying. I thought I was defining them from 128 and onwards. It looks like I actually defined them at 256, but I could have used 128. That area was free on all of the systems. It's just because the Master System and the Game Gear have twice the available tiles to the Game Boy Color, which only has 128. It looks like I chose a different number. But you'll see here we're using the tile number multiplied by 8, multiplied by 4. Well, why is that? Well, there are 8 lines in a tile, and each tile line has 4 bytes. That's because there's 4-bit planes per line. So we effectively multiply the tile number by 32. Because the tiles start at the top of the addressable memory, you'll see here the pattern definitions are the tile definitions. So they start at the top of the memory. So just by multiplying tile number by 8 by 4, or tile number by 32 if you prefer, loading that into DE, we define the correct destination address for the memory. We set HL to the sprite data, which you can see here is defined in that raw Sega Master System format, bitplane to bitmap, which is fine. And then the byte count is just the number of bytes we're going to send to the memory chip, to the VDP. So the define tiles function is very simple. We swap DE and HL because prepare VRAM will go to the memory address in HL, as we saw earlier. So we do need to swap them over. Then we swap them back because the prepare VRAM function doesn't change any of the registers, and HL will be intact. So now we load the first byte from our memory address, which points to our sprite data, and we write it to the VDP. And this is the VDP's data port. And the VDP's data port is BE. We're defining them as symbols here just for neatness here. So we just repeat until we've written all the data to the VDP and then return. And that's all we need to do to define a sprite. It's very simple. Now we're not going to look at how we actually get the fonts to the screen. Hopefully you can probably work it out. Essentially the character map starts at 32. So we subtract 32 and then set the tiles to the letters we want. Let's subtract 32. And we have to just fake some locate commands and cursor commands. The code will be in the example and we may well look at it later. So as I say, if you want to jump ahead and look at that kind of thing, just go ahead and look at it now. But today we're really just looking at the actual data job on the Sega Master System VDP. So once we've got the tiles defined, we now need to do this Chibico character here, and we do a bit of a trick. What we do is we define an area we want to fill, and I can show you that here. We define a starting position, so 3, 3. We define a size, so 6 wide and 6 tall. And then we define a starting tile, and as you can see, I actually started at 256, even though my example code here says 128. But it doesn't matter, you could change it perfectly easily. And what this fill area with tiles does is it uses all of the consecutive tiles to fill this area. So 128, 129, 130, 131, 132, 133, moves to the next line, 134, and so on. And that allows us to make this Chibico character, which is made up of a total of 36 tiles. And because the tiles are linear, we can just load in the bitmap data in a linear fashion. Really, the work of laying it all out is kind of being done by that sprite editor, the Akka sprite editor that I wrote, which I mentioned earlier, you can get from here. So it's this that's doing all of the layout work, and this is just showing those tiles to the screen in the same format. Obviously, if you changed this to 5 by 5, the character would get a bit messed up. Let's give it a go. So you can see the characters now got kind of jumbled up because the tiles are now too short. And if we changed it to you can now see it's now drawing two lines combined to one. So it is dependent on the format we're displaying it matching the format that it was encoded in by the sprite editor. But as I say, for an example like this, it's just fine. And now I'm only drawing half of it. So there we go. So as I say, it's pretty straightforward, and it's a nice easy way of working within the tile limitations of the Sega Master System, but drawing a bitmap graphic as if it was a bitmap display. Here's that command that fills the area with consecutive tiles. So you can see we've got BC as our start precursor position, we've got HL as our width and height, and DE is our start tile, which is 128 in my example on the website, but 256 in the code we're viewing here. But as I say, you can change it very easily, it doesn't really matter. So we have to just shift along our start tile position by the offset in BC. We use the get VDP screen pos, which moves the memory pointer to the tile we want to change. And then we just start writing our data. We're going to have a look at the tile format in a moment, but each tile is defined by 2 bytes, and then we just loop around until we filled the entire area. So let's have a look at that 2-byte definition. So here's a quite colourful example of it. So the high byte is here and the low byte is here. So let's have a look at the definition of the low byte and the high byte then. So as I've said before, the Sega Master System and the Sega Game Gear are quite good when it comes to tile ability, because they have a full 512 tiles, whereas the Game Boy Black and White only had 256. But because it's got 512, you know it must be using 2 bytes per tile definition. And that's what we can see here. All 8 bits of the low byte are the tile number, and also 1 bit of the high byte is also the tile number, and this in these 9 bits in total define a tile number from 0 to 511. We then have some nice flipping options, so we can horizontally or vertically flip a tile. Good if you've got a character turning around. We have a color palette option, because actually the Game Gear and the Master System can technically have 2 16 color definitions. One is always used by the sprites, and one can be used by either the sprites or the background. So if you set the color palette option to 0, it will use the first palette, which is the background palette. But if you set it to 1, it will use the second palette, which is always used by the sprites. There's no similar option for the sprites. The sprites always use the second palette. Next you have a priority option. This defines the tiles as going in front of the sprite or behind. So generally you'd probably want them behind, but you might want to have an effect where a character runs behind a tree, and you could put the tree in front of the sprites. And then you have 3 bytes that don't have any function at all. So that's the way we actually define the tiles and the tile map. But of course this code will do it for you if you want it in this simple function. Now, quite important, we want a way of converting an XY position in our BC register into a memory location, and we want the VDP to point to that memory location. And we use this for quickly drawing characters to the screen when you're printing your hello world type messages, and also for this function of drawing the tiles in a grid. Well, let's have a look. So as we said earlier, this is the memory map, and you'll see the tile map starts at 3800. We also have to do some tweaking because the Sega Master System screen is bigger than the same Sega Game Gear one, so we have to move the cursor along 3 lines down and 6 columns across to get to what is the actual top corner, the actual equivalent top corner on the Sega Game Gear compared to the Sega Master System. And this has the effect of meaning that 0, 0 is the top corner of either system. And that's why when I showed it you earlier, it looked identical on both systems, even though their screens are different sizes. Then what we need to do is we need to mess with our Y position. Now on the Master System and Game Gear, each line is made up of 32 virtual tiles. They may not all be visible, but it is made up of that. And each tile is made up of 2 bytes. So you need to multiply the row number by 64 to get the memory address, and then add the X position times 2. And that's effectively what we're doing here. We then add that to our start position here, and we call our prepare VRAM function. So that's all it takes to tell the VDP the correct memory location, and then we can just out the new information to select the tile we want to show in the tile map at the position we specified in BC. And that's really all it takes. So there we go. Well, I've gone through this quite quickly, and I'm hoping if you want to look into this some more, you'll download the source code and have a play with it. We will go over this again when we come to doing the printing of the text to the screen, because that also uses the tile map. The hello world messages, they are actually tile definitions as well. As I said, the fonts are definition, and so we're just plotting each of the respective tiles onto the screen here to get the effect you can see here. Next week we're going to have a look at the same function on the Game Boy, because as I've said, we're using the Game Boy in basically the same way. This fill area with tiles, define tiles, all of these functions exist in very similar format on the Game Boy, but the Game Boy is slightly different because it's actually memory mapped, so we don't use out commands to write to a VDP. But the procedure is basically the same. I hope you've enjoyed today's lesson. If you have, then please take a look at my Grime Z80 project, because that was also covering the Game Boy Color and the Sega Game Gear and Master System. And actually the code I showed you today was taken and enhanced and built into the beginnings of the Grime Z80 project. So it's the same code doing both. So if you are interested in seeing this code in action, or you didn't quite understand what was happening here and you want to see it used again, or maybe you're just not convinced it works at all and you want to see, really, can I actually deliver anything worthwhile with it? Take a look at the Grime Z80 project, because I think that was quite an enjoyable little game that only took me 7 days to write, and it did work on 11 different systems. So hopefully it proves that this code is viable enough to make something enjoyable and make something work pretty well. Anyway, I hope you'll join me next week, and we'll see the same on the Game Boy. But thanks for watching today. Please follow my channel and like this video, assuming you did like it, and goodbye now.